So spreadsheet exercise 3. So in spreadsheet exercise 3, a lot of the spreadsheet, almost all the spreadsheet has basically already been built for you. I wanted to provide the spreadsheet to you the way that I did so that you could kind of poke around at it and see how you would construct a spreadsheet like this if you were sort of just given this prompt from the outset. But at the same time, I didn't want to ask you to build a spreadsheet this complicated if, given this is like the third time you've maybe, poked around or worked in a spreadsheet. So essentially, what your task is, you have to go pretty far down in this document to find your exact specific task. But this walks you through the first few pages of this document, walks you through up until basically this last part here on page 7, how the spreadsheet was constructed and why. Okay, so if you have the time, try to understand why the spreadsheet is doing what it's doing, and that'll help you answer the questions that start on at the bottom of page 7 and go on to 8 and 9. Essentially, what you're being asked to do is model a future electricity scenario for the state of California. Where are we getting our electricity from in 2050 if we have this set of constraints? Imagine that the population continues to grow at 1% per year. Imagine that the economy continues to grow at 3% per year. Okay, and these are maybe sort of typical assumptions that you might make. That the future will look like the past. Okay, you look at the past 20 years of population growth in California, it's about 1%. So let's just say 1% continues on, right? 20 years of economic growth in California, about 3% per year. So let's just assume that continues on, okay? And how you would calculate what that would mean at 1% or 3% growth out to 2050, that's that first tab in the spreadsheet, okay? That's this one right here. So that's having the growth rate, the population and the economy as their own unique special cells. That's having the initial starting conditions here, population and GDP, as their own sort of hard-coded numbers, okay? And then after that, we're going to use a formula. We're going to use this formula right here, which is essentially the initial condition. Okay, so that's x0. So that's, in the case of population, 40 million, times 1 plus the percentage rate of growth. So 1 plus 0.01 in the case of population, which is basically just 1.01, okay, raised to the power of t. And t is just the number of years out in the future that you're interested in looking at. And so if t was 2, what you would basically be telling the spreadsheet is take that initial number, multiply by 1.01, and then multiply by 1.01 again, right? Because when you have something raised to a power, you're basically just saying, that's how many times I want you to multiply by this by, okay? Do it twice, do it 5 times. In the case here, we're going between 2020 and 2050, so do it 30 times, okay? The spreadsheet itself actually takes an iterative approach. So rather than raising to, the power, there's 2 ways to do it. The way that this spreadsheet does it is it actually uses this time column, and it does raise the initial condition C $5. So this specific cell right here multiplies that by the 1 plus the percentage raised to this power here. Okay, so this is the second year of the simulation or the model, and so it's raised to the power. There's another way to do this, which I'll put in this column right now just for giggles, is to have population start there and say we're going to multiply that cell by 1.01. Okay, Great. We end up with the same number as we had over here, slightly different formatting. But one of the things we can do is just drag this down, and we'll end up with the exact same numbers. And the reason is because the math is basically the same. What we've done, if you take the equation, this initial number multiplied by 1 plus the percentage of change, and spread that out, do that again, for example, right? Well, each time I do this, it doesn't matter what order I do the multiplication in. Okay, so I could multiply 1.01 by 1.01 and then multiply it by 40 million, and then multiply it by 1.01 again, and I would still get the same number as if I multiplied 1.01 by itself 3 times and then multiplied by 40 million. So the reason that this works is that I've basically said, okay, for this second cell here, what I've said is take 40 million, multiply it by 1.01, and then multiply that product by 1.01. Okay, and that's the exact same mathematically as raising it to the power of 2, raising 1.01 to the power of 2. Okay, so there's a number of ways that you could do that. This sheet goes ahead and uses that growth equation because I wanted you to see how that equation, what it looks like and how it would work in a scenario like this. And the same thing, happens for population as happens for GDP. We move down the sheet, and eventually we end up at our final population and final GDP per capita, because eventually we're going to care about the Kaya identity, which you learn about at the very beginning here of this exercise as you read through it, where essentially we take IPAT and we go one step further with it. Okay, we do impact equals population times affluence times, and then we break up the technology term into 2 different things. Okay, we say energy per unit of GDP, and then we do CO2 per unit of energy, because that even further breaks down the levers that we can use. We can not only can we change population and change total consumption or total economic activity, but we can also change the amount of energy that we use per unit of economic activity, and we can change the amount of CO2 per unit of energy that we use. Okay, so we have even more levers when we're talking about reducing CO2. All right, so the next thing, now that we know population, GDP per capita, next thing we need to know is energy consumption. We want to know how much energy, in this case, we're going to talk specifically about electricity, but we want to know how much energy today in 2020 is being consumed. Okay, if we're going to have the ability to say, well, this is how much energy per unit of GDP, we need to know how much energy. So we go to the EIA website and we find this chart and the associated tables, and it becomes pretty clear that there are really sort of 4 major sectors here: residential and commercial, so these are buildings, okay, and transportation. And then we have industrial, and industrial is its own kind of unique special category that includes not only the electricity and heating and cooling and so forth for the buildings that industry is occurring in, but specific industrial processes that themselves release CO2. Okay, and so for now, what this sheet asks you to do is to basically focus on 75% of this pie. It wants you to focus on residential and commercial as buildings, and then it wants you to focus on transportation. Okay, now there's also some fraction of industrial that is due to electricity generation. Okay, they're using electricity, absolutely. The thing is that we're not going into those specific industrial processes that by their nature generate CO2 and trying to decarbonize those processes. that's far too involved for what we're up to right now. So what you end up with is a tab here that for transportation makes a number of assumptions about how far people are driving, how many electric cars there are going to be, how much energy per vehicle mile traveled an electric car uses, okay? And all of those are based on reasonable assumptions, reasonable research that I pulled together, and in essence, identifies about how many vehicle miles are traveled in California today. You'd be surprised at how many different estimates there are of this, or maybe you wouldn't be surprised, but they actually range by quite a bit. Some estimates put vehicle miles traveled closer to this is in billions, so closer to 450 billion as opposed to 350 billion, and some of them put it lower, closer to like 280 or 300 billion. So this one seemed like a reasonable middle of the road estimate that was safe to go with. Similar here for kilowatt hours per vehicle mile traveled. That's an approximate value for today's batteries and today's electric cars. So there are some assumptions here about the improvements in the efficiency of these batteries. So the kilowatt hours per vehicle mile traveled goes down. We're using less energy over time to cover the same ground. And we are sort of reverse engineering the CAGR, the compound annual growth rate, if you recall that from the previous lecture, that would be required to go from 1% vehicle mile traveled as electric as it is today up to 100% by 2050. Okay. So you'll note that this is just one way of representing this increase in market penetration of electric vehicles. It probably won't work exactly like this. It probably won't be exactly like basically an exponential curve. It's more likely to be something like a logistic curve potentially, or it may look more stepwise. It may have, increase in plateau. But just for the purposes of estimating how are things going to look in 2050, this is a good enough approach. Okay, and what you have here across the whole spreadsheet is the initial vehicle miles traveled, some initial conditions about energy per unit mile traveled, the gigawatt hours that would therefore be required if we were to have a 100% electric vehicle fleet, where essentially we're saying this is how many vehicle miles are traveled, and we're going to go ahead and divide it by the number of kilowatts that would be required to move that many miles. And we're going to multiply it by how many kilowatts would be required to move that many miles. And then we're going to divide by 1,000,000 because we need to go from kilowatt to megawatt to gigawatt. Okay, so 1,000,000 kilowatts go into a gigawatt, 1,000 kilowatts go into a megawatt, 1,000 megawatts go into a gigawatt. So kilo, mega, giga, all right? And then finally tera, we get to terawatt. So we look at this and we say, all right, it's about 100,000 gigawatt hours. What does it look like as batteries become a little bit more efficient, cars become more efficient, people continue to drive? All right, we've made that assumption, at least in this initial scenario. People continue to drive more and more and more. And we have 100% penetration of electric vehicles. So all of transportation, we're just going to assume all of transportation is in electric vehicles, and it is all happening, and it's growing, and the amount of transportation that's happening is growing. And so we get about a little bit over 100,000 gigawatt hours out by 2050. So you'll notice then that the increase in the vehicle miles traveled barely outpaces the increase in efficiency of the batteries. And so that's why you get a slight increase in total gigawatt hours of energy demanded from the beginning to the end of the sheet. So that is simplifying, right? We're not trying to electrify air travel. We're, not building new light rail and blah, blah, blah. That comes in later and as the thing asks you to develop some different scenarios. So what about buildings? Okay. That is perhaps a little bit more straightforward, where essentially we're just saying that because we've done some other research looking at this specific report, which is very valuable, we've done some other research. That research shows that for buildings, we're going to need about 100,000 gigawatt hours of additional energy to convert all those natural gas appliances to electric power. But we're going to get some savings because everything's going to get more efficient. And so our total increase in gigawatt hours is about 80,000. Okay. And so how do we get to 80,000? Well, pretty straightforward. We go ahead and reverse engineer a growth rate using KGAR again, using the KGAR equation. And we go from 270,000 to approximately 350,000, okay, gigawatt hours per year for buildings. So total, what that looks like is this spreadsheet here, okay, where we're just adding what we had for transportation with what we have for buildings and industry. And that's going to give us our end goal. This is how many gigawatt hours we're going to consume, okay, out in 2050, right, in California. Little over 450,000 gigawatt hours, all right? So all that took some research, all that took some fiddling around in a spreadsheet, all of that took some basic assumptions, okay, some really kind of back of the envelope stuff, just picking like what's the sort of average of all of these other estimates that people have come up with. And the good news is that as a kind of truth test, this estimate is almost spot on for that you did on back of the envelope. This is almost spot on for what Mahoney et al. 2018 comes up with. And that's a really sophisticated analysis using some of the most advanced models and prediction software and data sets that are available for this kind of work. So now they get to this answer in some slightly different ways. What their model is able to do is far more interesting and elaborate than the one that you're building here. But at the same time, again, it should give you some reassurance that you're sort of on the right track, okay, for how much energy we're going to need out in 2050. Okay. And so now this is where it starts to get interesting. Okay. This is where it starts to get really sort of, at least I think, a little fun. Is we have this need for all this electricity. Where's it going to come from? Okay. The text of this paragraph kind of walks you through this sheet electric mix and describes the task, okay, that you've got in front of you. So I'm just going to walk through the 2020 mix and then talk about what's expected for this part right here, which is sort of the actual kind of assignment. It's where your assignment starts. Okay. So is this hard to read? Is it too small? So essentially what you have here is a column of notes, okay, that describes some things about these different energy types. You have the type of power, whether it's base load, intermittent, or peaking, okay? And these are important concepts that we talked a little bit about when we talked about the energy supply in those lectures. All right, peaking is stuff that you can turn off and on really rapidly when electricity demand suddenly peaks. Base load is sort of always there, it's always available. And intermittent is stuff that sort of depends on how much rain there's been, how much sun is shining, and how much wind is blowing. Okay, so those are your renewables, right? Most of your renewables are intermittent. So then we have our energy source, and that's described here. Fossil gas, natural gas, okay, coal, some other source, hydro, geothermal, biomass, including biogas. So this includes methane or quote unquote natural gas that has been generated from, say, a landfill or from digesting manure. Okay. We have nuclear here, and then we have wind farm and solar PV farms. With wind farm and solar PV farms, we have a certain amount of acres. Okay. And these are very, this is large. You can do it on less, but I wanted to, again, have some conservative estimates here that would sort of show how big the footprint could be. For the most part, this can be fewer than 5,000 acres. Wind farms can be fewer than 50,000 acres. These things can be packed pretty densely. Now, the more densely they're packed, the worse it is for birds and so on, and habitat and everything else. But if we're going for energy supply, then this is the kind of thing that we can do. We can make this more dense, but we spread it out for the sheet just to kind of make it a little more interesting. The next column over is the amount of CO2 per gigawatt hour. Okay. Now, for fossil gas, we're looking at half or thereabouts of coal. Okay. And for other, and we're just going to assume that other is gas. And the reason there's an other category is because we've gone to the California Energy Commission website, and there's an other category on the California Energy Commission website. And so this spreadsheet had to make some assumptions. I had to make some assumptions about where that energy was coming from. And the sort of most straightforward assumption that I could make was that it was basically, it worked out to being about natural gas. Okay. It was approximately what natural gas would be. Some of it's going to be coal, but some of it's going to be hydro. Okay. So how much CO2 is really being emitted per gigawatt hour of this other category, because it's all coming from out of state. We don't know what it is. Okay. When it crosses state line. So, I mean, sometimes we do, but for the spreadsheet, we didn't know. The website that I drew this from didn't say. And so we just assume that it's natural gas, right? Just keep it simple and assume that it's something that we can easily model and understand. The next thing here is something called the capacity factor. And the capacity factor is basically a scaling variable. It says, okay, yeah, I know that a coal plant can produce a gigawatt hour, a gigawatt per hour forever indefinitely. Like it's what's called its nameplate capacity. All right, that's the most power that it can produce at any moment in time is a gigawatt. But I also know that it's not running at full blast all day, all the time. I also know that it's, sometimes running at half power. Sometimes it's off for maintenance. Okay. And yeah, sometimes it's running full bore. So the question then becomes, what capacity factor do we use? And again, this came down to me doing some research to identify about what is the average capacity factor for a natural gas plant, okay, in the United States. What is the average capacity factor for a coal plant, for wind, for solar, for nuclear, for geothermal, for hydro, and so forth, okay? And these were the approximate capacity factors that were available, okay? So next column, we have the gigawatt capacity, the nameplate capacity for a given plant or farm of a given energy type. Let's just assume, since a lot of natural gas plants are small and peaking plants, and some of them are big, some of them are on the scale of gigawatts, but let's just assume that every natural gas facility is about half a gigawatt in terms of its nameplate capacity. And let's assume that every coal facility is about a gigawatt, okay? Every nuclear facility is about a gigawatt. And then let's assume that geothermal and biomass are also about half a gigawatt, okay? Some geothermal facilities are bigger, but a lot of them are smaller. Depends on the location, depends on the site, okay? Since biomass is going to be drawn, basically, we'll just say that it's largely the same as fossil gas, okay? We're going to keep it, again, about the same capacity factor, about the same gigawatts per plant. Now, the reason that I've done it this way is because embedded in this is a kind of naive assumption, a simplifying assumption that we can go ahead and just make methane. We can do biogenic methane and suck CO2 out of the atmosphere, turn it into methane, and burn that methane, have it release CO2 again, and have that be carbon neutral. Okay, so this is one of those useful simplifying assumptions that might make sense in 2050. Doesn't necessarily work right now that way, but in order to make this exercise useful, we have to make some assumptions about biomass. And that's one of the assumptions that I made. We're not just burning wood chips. We're not just burning trash. Okay, we're not just burning corn stalks and other, discarded agricultural byproducts. We're burning methane. Okay, we are taking the methane from our wastewater treatment plants and running it through a natural gas facility. We do that already. That's already something that's done on most wastewater treatment facilities of any significant size in the United States. It's good business for them. It makes a lot of sense. Landfill gas is another option. If you've ever driven by the landfills that are between Petaluma and Novato, and you've seen those concrete stacks that are just off-gassing methane, right? The fact that that's not being lit on fire and sent through an electricity generator is absurd. But it's expensive to get that stuff set up, and it's literally a dump. So what are you going to do? People don't like to pay a lot of money to throw trash away. So it's going to take regulation and other kinds of encouragement to get those things built. So we make some assumptions about the gigawatt capacity per plant. And then we have a column here that goes ahead and says, all right, well, that's how many plants we're estimating exist in California today, or are burning fossil fuels, or are generating electricity and sending it to California today. So in this column, we have the gigawatt hours of actual consumed delivered power to the in the state and to the state of California in 2020. Okay, we have about 100,000 gigawatt hours coming from natural gas. We have a much smaller fraction coming from coal and other sources. We have a 35,000 gigawatt hours coming from hydro, the second largest individual source, okay, of power in the state, hydropower. And then we've got some contributions from the rest. We've got solar, we've got wind, we've got nuclear, okay, and a tiny bit of biomass, and a tiny bit of and a little bit more, but not a whole lot of geothermal, okay. So the way that I structured this was to say, all right, here's our estimate of gigawatt hours, and how does that compare to the actual gigawatt hours? So you take the number of plants, you multiply by their capacity factor, and you multiply by their nameplate capacity. So I have 39 plants. Each of those can produce 500 megawatts or half a gigawatt of power when they're operating at full blast. Okay, so that's basically 20 gigawatts of total capacity, all right, that I could have. It's about 40 times half, 20 gigawatts of capacity. Now I multiply by the capacity factor, which is about half again. So it's about 10, 11, 12 gigawatts, okay? That's how much capacity. But how many hours are there in a year? Because we have gigawatt hours, right? We're not just gigawatts, we're gigawatt hours. So then we have to multiply by 8,760 because that's how many hours we have in a year, right? And we get a number that is very close to the real number. So although this is a little bit contrived in terms of the gigawatts, the nameplate capacity, the number of plants and so forth, we're getting a pretty close answer. We're getting an estimate in terms of the amount of energy coming from these different sources. It almost matches, almost exactly, okay? Very close, within a couple percentage points of the actual output. And so we know, therefore, that our model can be at least useful, even if it's somewhat wrong, even if the capacity factor is a little bit different in reality, even if the number of plants is a little bit different and the nameplate capacity is a little bit different, we know that we're doing something useful here, okay? Because we're getting close using reasonable estimates. Using reasonable estimates of nameplate capacity and capacity factor and the number of plants, we're getting very close to the right answer, okay? And so this, this allows us to get a total amount of CO2. We just take the amount of energy that we've generated, multiply it by the tons of CO2 per unit of energy, and we get tons of CO2. We add that all up, we get about 60 million metric tons of CO2 per year, which incidentally is almost exactly on the money, once again, okay? It's between 60 and 62 or so, okay, in terms of how much CO2 is coming out of the electric sector. So then we have this acres category, and this is just sort of an interesting constraint, right? I in the description of the exercise, I say you can't go above 3.5 million acres, okay? Let's just say that we're not going to do solar and wind at a scale larger than like 3 Sonoma counties, okay? We can blanket 3 Sonoma counties with wind and solar installations, right? But we're not going to go much bigger than that. That's the max, okay? Because otherwise, this exercise is kind of boring. It's say, oh, decarbonize the economy. All right, well, then I'm just putting solar and wind everywhere with no other constraints, right? So we're going to have a number of constraints as we move down into the rest of this sheet. And then we're going to think about cost, okay? So the 2050 model, what I have down here is almost exactly the same, except in yellow, I've highlighted the numbers that you should be changing in order to get to the target amount of CO2, which is 0, and the target amount of energy generated. This is here in green, which is again about 450,000 gigawatt hours. And I've also highlighted a couple constraints. I've said that your base load can't go below a certain number. I think I said 30%. You can't go below 30% for base load, and you need at least 20% for peaking, okay? People would, experts would probably argue, well, unless you have storage, batteries and whatever, you probably need more base load, and you might even need more peaking in the future of climate change, where there's going to be even more need for everybody to come home and turn on their AC all at once and so forth. But again, just to keep it simple, just to keep it manageable here, let's just say 30% base load, 20% peaking, okay? The other 50% can essentially be intermittent, okay? We're going to rely about 50% on other kinds of intermittent power. Or we could, if we want it. We don't have to. We can also use other forms. We can use biomass, we can use nuclear, and so forth. And again, we have to stay under 3.5 million acres, okay? So this is where you're going to be looking down here in this orange for the numbers that you want to see. The numbers you're going to be manipulating are up here. Since we know we're already going to be targeting 0 carbon emissions from the electricity sector in 2050, we know we're going to have no fossil fuels at all. We're not going to have any natural gas plants, any coal-fired power plants, or any imported energy that contains carbon. Okay, so those are going to be 0 and they're going to stay 0. I've already done that for you. This part down here just copies what we have today in 2020. And your job is to change these numbers. Okay, to change the number of plants that you're building in the state or out of state and importing the electricity in the case of nuclear, in order to meet your targets and stay within your constraints. So what are those targets? What are those constraints? Okay. You need, as I said, at least 20% peaking power. You need at least 30% base load, and you need 0 CO2 emissions. Okay, cool. We got those taken care of. All right. You can't have wind and solar farms take up more than 3.5 million acres. We've said that. Nuclear is fine. We can have nuclear power. We're just going to assume that it's imported out of state. California is phasing out nuclear power in state. Most of those nuclear power plants were built on the coastline. We have a very active tectonic fault along the coastline. They could have been susceptible to tsunamis, as Japan learned, and so they're being shut down. Doesn't mean that we won't necessarily build them in the future somewhere else in the state. The problem, of course, is we'll need water for cooling. Okay, nuclear power requires a lot of water for cooling. So if you're not building it on the coast in California, you're going to have a hard time finding that water unless you're tapping groundwater, and or importing water from somewhere else. Okay, so let's just say that there's nuclear power somewhere out of state that's being piped in. Okay, you can in the sheet you can say, yeah, there's going to be nuclear plants, and we just assume they're from out of state. We also assume that there will be no new hydro stations. All the good dam sites are already taken, so you can't increase the number of hydro stations from the 2020 conditions. All right, and that's generous. And the reason it's generous is because in the future there's going to be less water behind those dams, and so they're actually going to generate even less electricity than they do today. It's a consistent trend in hydropower in California. It's declining. Okay, it's been declining for at least since the year 2000, when the sort of long-term prolonged drought, people insist on calling a drought, when climate change really started to pick up here in the West. And because there are only so many places that we can build geothermal plants, the most we can build is 10. Okay, we're just going to say that the most geothermal you can have is 10, and that's it. And then finally, we have to keep total construction cost under $210 billion. So what does that look like? Well, just to kind of give you a start, right? If we say, all right, we're capped at 10 plants, let's just max that out right away. Okay, we put 10 geothermal plants in the mix. All right, what does that do? You notice that in this column, gigawatt hours estimated, I put 10 plants here. Gigawatt hours estimated goes up. Okay, goes from 13,000 to 32,000. The sum here, the estimated sum of total gigawatt hours generated, goes up by an equivalent amount. And then down here in the cost part of the sheet, we can see that geothermal plant capacity change is now 3. Okay, we've added 3 gigawatt hours of geothermal capacity. These costs are derived from the EIA, again, from their capital costs of construction. So this is just what it costs to build the facility, not what it costs to buy the land or lease the land, not what the fuel costs, you know, if it's nuclear or anything like that. This is just, I want to build this facility. How much does it cost to build it, given the size of the facility? So it's about $2,750 per kilowatt of installed capacity. Okay, this is just research that I did. You multiply that by the change in capacity, and then multiply by 1 million, because we're converting kilowatt hours once again to gigawatt hours. Okay, so that's the total cost. It's about $8 billion in 2020 dollars. I'm not going to make you deal with converting to 2050 dollars. In 2020 dollars, okay, that's about the cost. A little over 8 billion. Okay, to build those 6 geothermal plants. All right, so the next thing that you basically are going to end up doing here is fiddling around with the number of plants, the number of nuclear, number of biomass, number of wind farms and solar panels, or solar PV farms, in order, again, to make sure that this cost doesn't go over 210 billion, to make sure that you get a number that's within 5,000 gigawatt hours of this number here in green. We need at least 452 and at most 462, all right, gigawatt hours of electricity generated. We need at least 30% base load and at least 20% peaking, and we can't have our acreage go above 3.5 million. So for example, if I say, all right, I'm going to have 100 of those, and oh, looks like I can't build any more wind plants, right? Because if I build another wind plant, I'm over. Okay, so now I just have to leave that at 10. All right, well, what did that do? Solar PV. All right, 100 solar PV farms. Well, the problem here is that now my base load and my peaking are trash, right? And I need another 100,000 gigawatt hours. Okay, what do I do? Nuclear. How many nuclear plants do I want? All right, let's say I want 10 nuclear plants. Okay, let's say I want, 10 biomass plants. Okay, well, my peaking is still trash. Okay, and my base load is okay, and I'm doing all right on everything, but looks like I need more peaking. Where am I getting more peaking? Well, the only place I'm getting peaking is biomass. Okay, because it's basically a natural gas plant, except that natural gas is coming from carbon that's already in the atmosphere. So it's net zero. Okay, so what is that, 15? Okay, well, I still my peaking is too low. Okay, and I'm getting really close to my target in terms of gigawatt hours and my price. Okay, 20. Oh, geez, what about 25? Oh, geez, I can't do it with this current mix. I have to change these numbers. Okay, I'm under budget. I've got enough power, but I don't have enough peaking. But I have way more base load than I need. So what does that mean? That means I need to trade base load for peaking. Okay, I need to reduce my base load. I need to reduce my nuclear and get more biomass. Okay, so that's essentially how you go about this exercise. Okay, and it asks you to do a number of things once you've sort of done this once. Okay, you should save this as a separate file once you've gotten everything all lined up, once you know what these numbers should be. Okay, once you've gotten your energy mix figured out, you need to go and save this spreadsheet, okay, as a separate file, or you need to write these numbers down, because you're going to be asked to build, as your sort of actual submission for this assignment, you're going to be asked to build a report, okay, or at least build a document that has some graphs in it that use what you just made, this initial scenario, and a couple others. So there are basically 4 scenarios that you're going to have, okay? And that's described at the bottom of exercise 3. To keep it simple, table 1 helps you summarize it. I've given you the table. This is what I want to see filled in, okay? This is your baseline scenario. Vehicle miles traveled and buildings and industrial continue to grow as the state economy grows, as population grows, okay? So how many wind farms, how many solar farms, how many nuclear plants, how many biomass plants, and so forth. What is the acreage of wind and solar? What is the gigawatt hours per unit of GDP? And what is the overall cost? Okay. Gigawatt hours per unit of GDP, that can be found in Kaya. So this tab right here, this is updating automatically. As you change your spreadsheet, this Kaya tab is updating automatically. You don't have to touch it. You just need to look at it and write the numbers down. Okay. So gigawatt hours per unit of GDP right here, right? It looks super tiny. That's okay. I don't care how many zeros you got to write there. That's fine. Okay. If I was really mean, I would say convert that back to kilowatt hours, but I don't want you to have to lose any more sleep over unit conversions. The next scenario that you're asked to run is one where we continue to grow vehicle miles traveled. People still drive, but we go way above and beyond on buildings and industrial power. We do tons of conservation, right? We implement all kinds of restrictions and regulations and controls and prevent the amount of electricity that goes into buildings and industrial processes from increasing compared to today. So we cap it at 270 gigawatt hours per year. Okay. I want you to run that scenario. Now, quick trick, the way you do that is you go over to the buildings tab and you just say in 2050, that's how many gigawatt hours we're generating, because the rest of the sheet is going to refer to that cell. All right. I don't want you to go here and do the consumption growth. I mean, you could go up to consumption growth rate, you know, and say change that to 0. And now it's just 270 all the way down. You can do that. That's fine. Okay. When I fiddled around with this, I just changed this one to 270. Same with transportation. You know, I asked you at one point, what happens if we say that vehicle miles traveled is actually 50% of what it is today? Okay. We don't cap vehicle miles traveled. All right. We actually decrease it. All right. So, you know, you could say, well, what is 50%? How do I get to 50%? What's the CAGR needed to reduce 350 billion down to, you know, 175 billion? You don't even worry about that. Just come down here, go equals that cell times 0.5. Okay. 175 billion. Now, everything from here is going to refer to this cell, gigawatt hours for cars, right? So I go to gigawatt hours total. There it is, 45,000 gigawatt hours in that sheet. So there's a lot of moving parts, okay? And I can tell that Callie is exhausted already just thinking about how many moving parts there are. But poke around in it. I think you'll find that it actually makes some sense. I think you'll find that what I'm asking, once you've poked around in it and sort of understood, that coming up with these different scenarios actually isn't very difficult, because you already have the whole spreadsheet built for you, right? All you need to do is know that we need to change at some point when we're doing these scenarios. We need to change the total vehicle miles traveled to half. We need to have buildings be capped at 270. And then in one of the scenarios, we do both of those things. So that's like the super conservation scenario. Okay. And each time you do that, each scenario, then you can go over to your electric mix, and you'll notice that updates. So let's just say that I hard code this at 45,000. I hard code that at 175,000 or whatever. No, 270. 270,000. Okay. 315,000 gigawatt hours. I go to my electric mix sheet, and oh, look, that's the target now. 315,000 gigawatt hours per year. And so now I get to build this scenario all over again. Okay. But I do it with a much lower target. And each time, once again, I have to keep with the assumptions. Okay. Keep with the constraints of A through G. I have to have peaking power of 20%. I have to have baseload power of 30%. I have to have 0 CO2 emissions, and so on down the line. The only thing that changes each time I do these different scenarios is that I keep the cost of construction under different numbers. So for the first two derivative or other scenarios, I want it under 150 billion. I want to see you get this under 150 billion. And then for the last one, I want to see you get it under 100 billion. Okay. Once you do the first one, these other ones they're not nearly as difficult, because you've already done it, and you basically just sort of start subtracting plants until you get to the target that you need. So what do you actually have to turn into me? The below table filled in, table 1. Okay. I want to see a bar graph of the cost of each scenario. So that should be really simple. All I'm looking for are 4 bars, okay? Under each one, I just want to see scenario 1, scenario 2, scenario 3, scenario 4. And the height of the bar is just how much it costs. So overall cost right here, right? Overall cost right here, whatever that is. Let's just say that we have scenario, we have cost, what was it, 210 billion. Okay, let's just say 210, just to keep it easy, 150, 150, 100. Okay, scenario 1, 2, 3, 4, or let's just say A, because that's not going to confuse Excel. All right. I want to insert a chart. I want a bar chart. Boom, done. Okay, that's what I mean when I say bar chart. I just want to see the chart. I just want to see how the cost is different under these different scenarios, right? The next thing I want is a pie chart of the energy mix as a percentage, and I want it for each scenario. So each scenario gets its own pie chart. So what does that look like? Well, if I take electric mix, okay, and I go to gigawatt hours estimated right here, and I say, hey, I want a pie chart of that. Okay, now I need to label it because right now it looks like trash. I don't know what any of these are. Okay, a better pie chart would be to say, all right, gigawatt hours estimated. Okay, I want to paste the values, right? Energy mix. Right there. Okay. I'm going to go insert a pie chart. There we go. Okay. Maybe I want to label the percentages. Boom. All right. So you've built these kinds of charts in the other exercises, right? So I'm just asking you to refresh that and go ahead and do it for this. And then finally, I just want to write up a 200-word description of your results, okay? And specifically, I want you to respond to the question, what are the trade-offs between the different energy sources in terms of cost, acreage, installed capacity, and capacity factor? Because one of the things you're going to run up against, right, is, okay, well, nuclear is great for base load especially, okay, because it has a super high capacity factor, and it's a pretty high capacity per facility, right? It generates a lot per facility. But nuclear costs a lot of money. Okay, nuclear is not cheap. If you go to the cost portion of this sheet, nuclear is the most expensive by far. Okay. Now solar is the cheapest, so that's great. But of course, it has a terrible capacity factor, 25%, really low. Okay. And so that means you have to build a large amount of the plants, and that butts up against your acreage constraint. Okay. And so the thing I want you to see, or one of the things I want you to get out of this, is recognizing that, and this is just dipping your toe in, because there's a lot of other constraints, you know, that for like that big report that I linked to, the 2018 work for the governor's energy office. You know, there's a lot of other constraints in the system beyond just cost, acreage, and capacity factor. Okay, there's siting. Where do you put it? You know, I have the whole like, oh, there's 10 geothermal plants, and it's sort of just like, yeah, okay, there's 10 plants, but like you build them far away from everybody. There's line losses. How much energy is lost as you're transmitting the energy from one place to another? You know, peaking and base load, these are actually often very different plants. Like I've kind of homogenized them here. I've brought them together. But a natural gas peaking plant is a very different kind of plant than a base load natural gas plant. Okay, and I've just kind of homogenized it and said it's the same thing for simplicity's sake. Okay. And like I said, with hydro, there's trade-offs with how much hydro you can generate depending on how much water you want to be able to send down the river for farmers or for cities. Okay, so there's all kinds of other trade-offs here that I'm not having you address, but I do want you to just see that there are trade-offs, and some of the big ones are space, cost, and ultimately the efficiency. Because again, you build 10 nuclear plants and you get like the same amount of energy as you get 78,000. How many solar farms do you need for that? Let me guess. Something like 40. Okay, yeah, you need like 35. Okay. So you've got 10 nuclear plants, and those can all exist on like a very small number of acres. Okay, 100 acres a piece or something like that. Whereas here we've got 700,000 acres of solar panels. Okay, like huge difference, huge trade-off in terms of how much space you're asking the planet to hand over to generate the same amount of electricity, right? So, I didn't have anything in here. There's no trade-off in here about, well, what happens to the nuclear? What happens if the uranium supply chain is interrupted? What happens if, the solar panel supply chain is interrupted? What happens if there's a nuclear meltdown? What happens if a natural gas plant explodes? Like all those health and safety trade-offs, all those like geopolitical trade-offs are not in this scenario. But there are all kinds of trade-offs that this scenario sort of helps you start to see. Okay, so that's it. That's the assignment. Are there any? And it's worth double. It's worth double what your other two assignments were worth. So this is worth 20 points as compared to 10 for your previous spreadsheet assignments. So it's worth those two previous assignments combined. Still, it's the same as a Pearson reading, and so forth. So, get in there, play with it. If you can't, get all the way there, don't hesitate to ask me for some help, because I have the numbers that I came up with. Okay, like I solved the scenario, of course. I built it. I hope I did. I made sure that it worked, that it's actually possible to do this. So, if you get stuck, let me know. Send me your spreadsheet and I'll say, hey, it looks like, try a little bit less nuclear and a little bit more biogas, which is probably going to be what you're going to end up having to do. A little less nuclear, a little more biogas. That's my guess. So are there any questions?